So in this lecture, we'll talk about epoxides. So epoxides are special class of ethers. For example, if you consider ethers in general, these are open ethers or the non-cyclic ethers. So epoxides are cyclic ethers. So here the size of the ring determines the parent name of the molecule. So if you have a 2 carbon rings, if you have a 3-membered ring, that's an oxyrane, 4-membered ring is an oxetane, 5-membered ring is an oxalane, and 6-membered ring is an oxane. So because the others are not that reactive, we'll try to focus more on oxyrane. So this is considered to be more reactive. The reason is because there is a significant strain on the ring. So because there is a significant ring strain, so we'll try to focus on these. So oxyranes are also called epoxides. So that's where the name comes from. Now, so any typical epoxide generally has 4 side chains, can have 4 side chains. If you take all of them to be hydrogens, the compound is called ethylene oxide. So ethylene oxide is a oxyrane with hydrogens. Now, although these are generally unstable, epoxides are generally commonly found in nature. So for example, disperlure is a sex pheromone of the female gypsy moth, and periplanone B is a sex pheromone of the female American cockroach. So most common use of these is understanding if the inhibition of these sex pheromones can help in, for example, let's say if you wanted to kill a cockroach, one way of doing or killing the male cockroach is to make a compound that resembles periplanone B and lure them in and then feed them with some poison or something so that you can kill them out. So this is one another example of where you can see insecticide materials. So epoxides in general are generally much strained. So this is the main reason why epoxides are much more reactive, and that's the reason why because they are generally unstable. Now let's try the nomenclature. So there are 2 ways of naming them. One, you can consider the epoxide or the oxygen to be a side group, and or you can consider the oxyrane itself as the parent name. So let's take an example of this compound, so the common compound. So you can name the numbers based on the numbers in general cycle, and notice that you are trying to give the least number to the oxygen, so you are going to go in the reverse direction. So you're going to name the so 2,3 locant as an epoxy. So when you write epoxy, it means that there is a cyclic ring there, and the rest, so you have on the 3rd carbon there is an ethyl group, and on the 2nd carbon there is a methyl group. So it becomes 3 ethyl, 2 methyl, pentane. So pentane with a total of 5 carbons. Or the other way of naming them is take the cycle itself as the main chain, and you can consider that it's 1, 2, 3. So the reason why you give 2 here in this order is because notice that there are longer carbons on 2 than that on 3. So you have to give the alphabetical order. So ethyl is comes before methyl, so you give the lower number to ethyl. So it becomes 2, 2 diethyl, 3, 3 dimethyl oxyrane. So oxyrane is the name used when you use it as a parent name. So for when you use it as a substituent, we use the suffix epoxy. So use the prefix epoxy. Now, how do you prepare epoxides? If you remember from reactions of alkenes, when we talked about the epoxide formation, when you treat an alkene with a peroxy acid. So when you treat an alkene with a peroxy acid, you end up with a epoxy compound. So the most commonly used ones are MCPBA, which is metachloroperoxybenzoic acid, and peroxyacetic acid. So notice that any peroxy acid is basically R with a carbon, double bond O, oxygen, and another oxygen, hydrogen. So this here, bond C double bond O, OH is the name for peroxy acid. So I already told you that when we discussed in the topic about ethers, I told you that peroxides are generally less stable, and they are generally they are readily reactable. So what happens here is that if you take an alkene, a cis alkene, and mix it with MCPBA, which is metachloroperoxybenzoic acid, and you end up with a cycle where it takes the double bond itself as the oxyrane ring. So it creates the oxyrane ring at the double bond and bonds it with the oxygen, creating a front and back structure for the hydrogen and R. So the ones at the bottom come front and the ones at the top go to the back. So in the same way, when you do it with the trans compound does the same thing with MCPBA, but the difference here is that whatever is in the bottom again will come front, whatever is in the top will go in the back. So this is the reaction for epoxidation. So this process is called epoxidation of an alkene, and this process is stereospecific, meaning that it determines which type of configuration you have that you end up with. So you always have, if you start with a cis compound, you will end up with a cis compound. If you started with a trans compound, you will end up with a trans compound. So epoxides can also be synthesized from halohydrins. So halohydrins, if you remember, are compounds with halogen and an OH group, a hydroxyl group. So halohydrins are generally synthesized from an alkene. So once we create an halohydrin, if you add NaOH to it, that results in the formation of epoxide. So how does the mechanism work? So there are two main mechanisms that undergo here. So the number one is photon transfer, proton transfer, and number two is intermolecular SN2 reaction. So let's look at the reaction in real. So we have a halohydrin. So this is the first compound. Notice that in this structure we start with a general halohydrin. So here you can have OH group is in the front or on the back. It can be on any side. Now once you have the halohydrin, so let me use according to the example that's given. So you have the halohydrin. So this first undergoes a reaction with NaOH. So for the NaOH reaction to occur, so give me a second, so you have NaOH. NaOH splits into Na plus and OH minus, where the oxygen gets 6 electrons with a negative charge. So if you already remember, OH minus is a compound that's always ready to attack a proton. So the proton here comes from OH. So the oxygen that has 2 lone pair of electrons is bonded to a hydrogen. So this OH minus attacks the proton. So now the 2 electrons are given back into the oxygen. So this results in the formation of so it has oxygen with 6 electrons and a negative charge, and you also end up with a bromine. So that bromine here stays there. So if you remember that bromine in itself already has 6 electrons, so it has 1 electron that's being bonded. So the excess electrons, what they will try to do here is the excess electrons will try to go away towards the other side. So this is called as a intramolecular SN2 reaction. How does this work? So let me draw it in a 3-dimensional structure. So if you remember that this here is the structure that we draw for, or the base configuration for a general compound of cyclohexane. So the cyclohexane here, there is one on the top and one on the bottom. So look at here. So notice that this here is the bottom part and this here is the top part. So which means that here you get the oxygen. So this here is the oxygen with 6 electrons and a negative charge, and on the bottom you have a bromine with 6 more electrons, and so this 6 more electrons. So what happens here is that this compound now donates its electrons towards the compound. So this basically donates its electrons. So this compound donates electrons to bromine, this carbon. So the carbon then donates its electrons back to bromine. So this results in the formation of, so where the bromine will go out with bromine with 8 electrons will leave the compound, and it creates, so this creates a structure where this carbon, so this carbon here bonds with the oxygen. So now you end up with a structure where you see a cyclohexane, where notice that this is the first bond. So notice that this is on the top, oxygen. So the other side also wants to bond with oxygen. So what it will do here is it will bend the compound towards itself, so where the oxygen exactly comes in the middle, and both the carbons will try to bond with the oxygen. So this here is what happens after that reaction. So this reaction, what you saw here in this compound, is called intramolecular SN2 reaction. So this is the reaction of preparation from halohydrins. If this reaction looks similar, notice that this is actually the same reaction as the reaction that you saw in Williamson's ether synthesis. It's the exact same reaction but applied to epoxides. So here the intramolecular SN2 reaction happens because of the presence of that extra oxygen. That extra oxygen not able to leave but still having extra electrons. So these extra electrons will try to come to this carbon and bond with the oxygen. So creating this unstable oxidane structure. So this is how the final reaction generally occurs. Now there is, so the preparation of epoxides. So you have the note that you can create it from either route. So where you can create from an alkene to epoxide, which is going to be stereospecific, meaning that wherever you go from cis, it goes to cis. It doesn't matter which reaction it is, even if it is Br2H2O and NaOH, it still occurs the same way. So the next topic is enantioselective epoxidation. Remember that we talked about stereospecific reactions. Here we want to talk about enantioselective reactions. Enantioselective here is that epoxidation methods we have discussed so far are not enantioselective. Here enantio basically refers to the chirality of the carbon. So the epoxidation of an achiral alkene produces a racemic mixture. So when you have an achiral alkene where there is no achiral center, the compound will end up forming a racemic mixture of both compounds, where you end up with the compounds going front and back. For example, in the first compound, methyl is in the front, ethyl is in the back. But in the second compound, ethyl is in the front, methyl is in the back. So in the same way, methyl is in the back and the isopropyl is in the front, and here isopropyl is in the back and methyl is in the front. So this is a racemic mixture of R and S. So it creates a racemic mixture of R and S. This is the process of enantioselective epoxidation. Now when you take enantioselective epoxidation, the epoxidation in general forms a racemic mixture because the alkene can react on either phase. Because remember that alkenes have a flat structure. So alkenes have a plane structure, a planar structure. So which means that the oxygen, the compound that reacts the oxygen, the oxidane structure, oxidane ring, so the oxidane ring can form on top or on the bottom. This is the reason why the reaction is going to form a racemic mixture. So if you want to create only one phase, what we have to do is we will have to use a chiral catalyst. For example, let's say you want the ring to be only on the top or only on the bottom. The only way you can do that is to use the chiral catalyst. So one of those chiral catalysts is titanium tetraisopropoxide. So this is called as the sharpless catalyst. So it's a chiral complex of titanium tetraisopropoxide and diethyl tartrate, so DET. So the two compounds, what they'll generally do is this catalyst will basically cause an enantioselective epoxidation of generally an allylic alcohol. Remember that this is the main point. So this can only occur when you have an allylic alcohol. Now, if you have an allylic alcohol, what will happen here is the enantiomer of the catalyst. So if the catalyst DET will favor the formation of the given enantiomer of the epoxide. For example, if you have a positive DET, forms the epoxide above the plane. If you have a negative DET, always creates the epoxide below the plane. So depending on the type of DET that you use, you end up with the final compound that resembles your final product. So now you end up with 98% enantiomeric excess of one of the compounds. Either you get it totally on the top or totally on the bottom, depending on the type of the positive or the negative DET that you use, you end up with. So the diethyl tartrate that you use gives you the enantiomeric selectiveness. Next, let's talk about ring opening. So the reactions of epoxides are more commonly called the ring opening reactions. The reasoning here is because epoxides, because they are unstable, they will always try to open that ring because of high significant ring strain. So because of that significant ring strain, epoxides are generally reactive towards weak and strong nucleophiles. So the more common of them are Grignard reagents, hydride reagents, alcohols, and alkoxides. So epoxides are also used for useful synthetic intermediates. So for example, an example of looking at a strong nucleophile is if you take an OH minus group. An OH minus group will always attack one of the carbons that bonds to the oxygen and create an alcohol group and separates the ring from the structure, creating an O minus. This O minus again forms under proton transfer, creates diols. If you remember, this is one of the reactions we talked about in the alcohols, where you can create diols by using epoxides. So let's look at the reaction much closer. So let's say I have an oxirane So this oxirane here has two lone pairs of electrons, and what will happen here? Let's take an example of OH minus. So the OH minus group, so it will attack the carbon. So this will attack any one of the carbons. For example, let's say it attacks this carbon. So when it attacks the carbon, it opens the ring. So what will happen here? These electrons will go towards the oxygen. So this creates the structure of O minus, and it creates a plain ring with another OH. Now this structure, because of the negative charge, it will react with a H2O molecule, so a water molecule, and this undergoes proton attack. So it will attack the proton, and the electrons are given to the molecule O again. So this creates an OH minus molecule again. So notice that the OH minus molecule is the one that gets created under proton attack, and finally forms an OH on the top. And an OH on the bottom. So this is ethane diol. So because there are two carbons, so this is an example of a compound of ethane diol. So you started with an oxirane, and under reaction with OH minus, it creates a diol. So it creates a diol. So you started with an oxirane and you end up with a diol. So let's look at ring opening reactions of epoxides. If you look at the reactions energy, the ether with NaOH has really low energy. It starts at really low energy. That's the reason why ethers are not that reactive to form alkoxide ions. But when you look at the same thing with epoxide and NaOH, they have a really high starting energy, meaning that the amount of energy that they require to reach the peak is much less. So that's why it's much more thermodynamically favored. So what are the common ring opening reactions? So the first, when you use NaOR, so for example, if you take sodium, so if you take any alkoxide material, it generally reacts and forms what we generally call an alkoxide at the end, and it creates an ether and an alcohol. And if you use cyanide, it creates cyanoalcohol. If you use SH, it creates thioalcohol. If you use a Grignard reagent, it creates the Grignard compound attached to and creates an alcohol. And if you use lithium aluminum hydride, it generally creates an alcohol. So these are the common reactions, and the ring opening of an epoxide is generally regioselective and generally going to be stereoselective. So it always tries to use regioselectivity and stereoselectivity. So it can be done with many strong nucleophiles. So let's talk about regioselectivity. Epoxide ring opening is an SN2 reaction. So the least hindered carbon is generally going to be the most reactive towards the strong nucleophile. So here the least hindered carbon is, if you look at this carbon and this carbon, so whichever is the least hindered carbon is the one that's going to get attacked by the nucleophile. Here this position is less hindered, so the nucleophilic attack's always there, right? So that creates the nucleophilic reaction there. And the other side creates an OH group. So this is the common sense of the nucleophilic reactions. So in terms of stereoselectivity, because of the SN2 reaction, there is an inverse of the configuration that generally is observed. For example, if you take the carbon that's least, for example, if you notice that there are two side chains here. Here this is the less hindered carbon, so the attack takes place at that chiral center, and when that takes place, it changes the stereoselectivity of that compound. The oxygen will stay on the top with as an OH group, but the bond where it forms the reaction, the nucleophile attacks, creates the opposite change, so the configuration will be inverted. The reason it's inverted is because it's an SN2 reaction. So if you remember that SN2 always creates R to S or S to R. So it's always going to change the conformation or the configuration of the chirality center. So let's look at acidic conditions. So what happens during acidic conditions? So acidic conditions can also be used to open epoxides generally with weak nucleophiles. For example, HCl, HBr, water or alcohol. So let's start with the reaction. So the first thing that happens here is, let me write it down separately. So if you look at an oxirane, so notice that we took the oxirane here. So oxirane gets attacked by a general alcohol, let's say a hydrohalic acid. So the hydrohalic acid, again, what will happen here? So it has to undergo a nucleophilic. So first it undergoes a proton transfer. So the proton transfer occurs because the oxygen attacks the hydrogen, and the hydrogen will donate its electrons to the the halogen. So that creates the oxonium ion, again oxygen with a hydrogen bond and 2 electrons and a positive charge. Now it will create the X minus. So the X minus that it creates attacks any one of the carbons, because notice that it always attacks the less hindered carbon. So both are less hindered, so if you consider that any one of them will get attacked. So when that gets attacked, the oxygen with a positive charge and a hydrogen attached now has an X attached to it. So the X attached causes it to split the structure, because notice that these two are donated to the oxygen. So when it attacks, so now so here this donates its electrons here. So now it opens up and creates an OH group on one side and creates a X on the other side. So this is the reaction that generally occurs. So the second reaction here, the first reaction is proton transfer, and the second reaction is the SN2 attack of the nucleophile that's attacking the, so this here is the nucleophile that's attacking the less hindered carbon. So what are the other forms or other ring opening reactions? So water or alcohol can also be used as a nucleophile under acidic conditions. So when you use it under acidic conditions, the same thing happens. The first thing that happens is it creates a the structure undergoes a ring opening by first undergoing proton attack, and second it undergoes an SN2 attack. So both of them happen, and when you mix it with water, it undergoes OH diols, it creates a diol, and when you mix it with an alcohol, it creates a ether and an alcohol group. So basically it creates a so on one carbon it attaches a alkoxy group, and another carbon you will have a hydroxy group. So this here is the idea behind the structure. So best example of this is antifreeze. Antifreeze is the compound ethylene glycol that's commonly used. So it's generally made industrially by this method. So when you use ethylene oxide and react it with water in presence of H2SO4, it creates ethylene glycol. So the ethylene glycol is used as antifreeze to coat on airplane wings to make sure that the ice does not make the wings brittle. So let's look at the acid catalyzed mechanism. So you have the oxidant ring structure. So the oxidant ring. So the oxidant ring. So the first thing that happens is because of the presence of acid, it creates H3O plus. So the oxygen attacks the proton donates its electrons to oxygen. Now that creates H2O. So that goes out as H2O. And this ring structure creates oxygen with a hydrogen, 2 electrons and a positive charge. So this creates an oxonium ion. This oxonium ion next undergoes an SN2 attack from the water molecule in itself. So the water molecule attacks one of the carbons. So when it attacks one of the carbons, so it creates the structure. So when it attacks one of the carbons, the carbon will donate its electrons to oxygen. So this creates the structure where you have the 2 carbons. So on this side you get oxygen with 2 electron pairs and hydrogen, and on this side you have an oxygen that's connected to 2 hydrogens again with a positive charge. Next, if you take any other water molecule, so this undergoes a general reaction where it undergoes a proton transfer again. So what will happen here? This structure will take up, if you take another water molecule, so any other water molecule will attack the proton structure and it donates its electrons to the oxygen. So with creating the final structure where you get an oxygen, so it creates a diol. So first thing is proton transfer. So the second thing is an SN2 attack, and the third one again is proton attack. So these are the 3 main processes or 3 main mechanisms that occur in the reaction of creation of a compound. So there are 2 proton transfers and 1 SN2 reaction. Now, so ring opening under acidic conditions, so the nucleophile attacks the less substituted carbon if it's a primary or a secondary carbon. But the problem is if you have a primary or a secondary carbon, so it will always attack the primary carbon because it's going to be less hindered. So if you take HX, X will always attack the primary carbon. But if there is a tertiary carbon that's present, then the nucleophile attacks always on the tertiary carbon. This is a peculiar form of a nucleophilic reaction. Notice that this reaction is what we call the SN1 reaction. So if you have a tertiary carbon, it undergoes an SN1 reaction where the nucleophile, rather than attacking the primary carbon, will attack the tertiary carbon. So remember this, if it's a primary or secondary, it will always choose the primary. if you have a primary or tertiary or a secondary or tertiary, it always chooses the tertiary carbon. So this is the reactions. Now, since the epoxide itself is cationic under acidic conditions, so there are electronic effects that result in the CO bond to a tertiary bond to be weaker. So because of the presence of that tertiary bond, so the dominant factor here is the steric effect. So notice that if you have a tertiary carbon is not present, then the steric effect will dominate. Right? If there is the tertiary carbon, the electronic effect will dominate. This is the reason why the tertiary carbon will get attacked if you have a tertiary carbon that's present in the compound. So now, if you take this compound here, here you have a primary carbon, and you have a this is a secondary carbon, and you have a tertiary carbon. The attack happens at the chirality center of the tertiary carbon, where it flips the structure and changes the configuration. So remember that methyl was on the bottom. Now methyl goes to the top, and OR attaches at the bottom. So why is it OR? Because it's an alcohol. If it's H2O, the compound that gets attached is OH. If it's an alcohol, the compound that's attached is OR. So it creates the alkoxy compound that gets attached. So, and the inversion of the configuration.